So years ago, before I was full-time faculty here, I took a semester somebody had a tree fall on him. And so actually I subbed in his class. And bottom line is when it comes to this test, the student had his calculator out, having a meeting. And so he was like furiously putting things in his calculator. And I got to thinking, you don't need a calculator for this test. What are you doing with your calculator? So anyway, yes, it was one of those nice programmable ones, and so he had pretty much periodic table in his calculator, which I don't know. Anyway, true story. So we're gonna look at something that a lot of times students coming to this class have already looked at before, and so I kind of have an uphill battle to make it interesting and to try to give you what you need for college general chemistry with regard to the electrons, and so you'll know what I mean when you see it. So here's the deal. Here's an atom through time. And actually, I think let's get that little video. But what we used to think about an atom. So for instance, back in 1803, Dalton's model of an atom was that, hey, matter's made up of atoms. He wasn't in 1803 the first person to think of that, but he kind of kicked off, and we talked about Dalton's atomic theory. And then in 1904, which is like 100 years later, right? If you compare these two pictures worth 1,000 words. The difference is with Thomas in 1904, we have now an atom, but we have pluses and minuses. We have little subatomic particles, okay? The problem with Thomas's model is, as we know, the atom is not organized this way. Atom has a nucleus, and inside the nucleus we have the positively charged protons, outside the nucleus we have electrons. And then Rutherford, just 7 years later, finally said, all right, I get this. So here, the two colors of purple, the dark color purple in the middle is the nucleus, which we have the positively charged protons, and then kind of this fuzzy looking light purple, that lavender, that is actually where the electrons are located. So a big breakthrough there. Sometimes Thomas's model is called the plum pudding model, which is kind of fun. Like those would be like raisins or nuts or whatever in plum pudding. And we know that, of course, the electrons are outside, the protons are in the nucleus. Then the difference between Rutherford and Bohr model, can you see where that fuzz, that light purple, actually now has little orbs? And these little orbs represent the electrons outside the nucleus. And the big thing here, and this is very true, so we're getting down to kind of the modern day view of the atom, but we say electrons can be at these energy levels. So that's what we call quantized. So an electron can be here, and next, closer to the nucleus, will have lower energy, or an electron can be out here, farther from the nucleus, will have more energy. So Bohr, we'll talk about Bohr model of the atom, and we know that electrons actually have different energy levels. Then this is the latest, and it's the Schrodinger model. And the difference between the Bohr and the Schrodinger is, kind of makes me itchy sometimes. You can kind of see these sort of bands. These little dots are where the electron might be. Okay, so that's a Schrodinger model. It's what we call an electron cloud. So we're like, it could be anywhere here, okay? Not that there's that many electrons, but it's like if we here, they're kind of jumping around. Electrons are a jumpy sort of subatomic particle. So those are the models over time. So for instance, with Thomson's plum pudding model, we can have this sort of thing. If we find helium on the periodic table, it's atomic number 2. Atomic number 2 means it has 2 protons in its nucleus. So Thomson recognized that, and Thomson said, well, if it has 2 electrons in the pudding, remember this is before we knew about electron cloud and all that, he said then the 2 pluses it has are kind of counteracted by the 2 minuses it has inside there, and it's neutral. So actually we have helium, that's a neutral atom. We say if it kicks off, if it loses 1 electron, see, compared A, the first one to the next one, it loses 1 electron, now it's actually got a +1 charge, helium +1. If it lost both electrons, it would be helium +2, which is kind of a strange thing to think about. That's not a very common thing, so you would have to force it, but it's possible. So that's kind of Thomson's model. This is a little bit of a wrong sort of deal too. Now this would be where we have the nucleus, protons in the nucleus, along with the neutrons in the nucleus. and the electrons are outside. The problem with this is a couple-fold. One is that it's more like a Bohr model where it's, well, I don't know, it's just showing electrons outside. I don't know if those are necessarily different energy levels. If you read the caption, this is kind of interesting. Now, not as it's projected, but as you would see it down here, if you take that period, and that period is the volume of the nucleus, then the nearest electrons would be a 5 meters by 5 meters room. You know, electrons are in a sphere, basically. We're going to see it's not always a spherical shape. But if you take a 5 by 5 meter room, and this might be 5 meters, pretty square. So put that little period that's on there right there, and that's the nucleus. To scale, then, the closest electron would be purple. Here, then, we're getting to definitely kind of a Bohr approach where electrons have certain energy levels. So in the middle here, that's your nucleus, okay? And the electron can be here, it can be here, it can be here, okay? These are here in a minute what I'm going to say principal energy levels. So the variable for a principal energy level is the variable n. So we have here n is equal to 1, you know, maybe this is it. Because n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. So those are where an electron can be. There's a certain amount of energy associated with that. So again, with the Bohr model, the only thing between the Bohr and the Schrodinger is the Schrodinger kind of gets that sort of cool, ghosty looking electron cloud where the electrons are going to be. But so hydrogen is atomic number 1, has 1 proton in its nucleus. If it's neutral, it has 1 electron, and there's where that 1 electron would be. We increase by atomic number 1 to helium. Now it has 2 electrons. Okay, this is now period, this is period 2. The first one's period 1, this is period 2. Remember, periods go across. Those are our rows. So we have atomic number 3, 4, 5, 6, 7, 8, 9, 10, you know, lithium through neon. And you can see where the electrons are being added. Actually, I'm finding some noise out there today. Actually, the electron in blue is, I think this is right, is what we call the valence electron, or electrons. We'll be talking more about that. Period 3, okay, and you can, this is kind of exciting. So like for the instance, these 18 electrons around an argon atom with 18 protons, you can kind of see how the electrons are in their principal energy level anyway. And actually, we're going to kind of break the principal energy level up into something a little more fancy behind the scenes. So these N principal energy levels are going to be broken up here in a minute. Period 4, a couple of metals look like this. This has got one of my favorite phrases. Let's see if it plays.
Protons and neutrons.
Yep, protons and neutrons. Very good. Electron cloud. Good. Okay, so I said you don't have to use your calculator for Unit 4. One of the things we're going to get hot and heavy into in Unit 4 is basically how atoms join together to make a compound. Like for hydrogen, H2O, how do those 3 atoms get together to make a water molecule? And we're going to see that it has to do with the electrons. So we're going to focus a lot on the electrons. So just like beginning with the Bohr model, we know that electrons aren't willy-nilly. You can actually point to a carbon atom. Carbon's atomic number 6, so if it's neutral, it has 6 electrons in a cloud outside its nucleus. You can point to those individual 6 electrons, and we can actually say, we can assign a lot of information, including energy, and general location, not specific location. So the energy that an electron has is quantized. So what do I mean by quantized? So quantized, and you're going to see here in a minute in terms of like a stairs, if you're walking the stairs, okay, you can be here, or you can be here, or you can be here. You're walking up the stairs, but it's different than, so these are discrete elevations above the floor. So it can have discrete values, but not any value in between. So here we go. Here's my chemist here. Okay, he can only be on one of these 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 positions. He can be one of these 5 positions. But this chemist over here has like an infinite number of places that they can be. And again, with regard to, you can call it stored energy, potential energy, how far above the floor are they? This guy only has 5 choices, this guy has a whole bunch of choices. This guy's energy is quantized, that guy's energy is not. So with regard to the energy of an electron, I call this the couch potato stage, okay? So electrons have some options, okay? We saw a minute ago that they can be at n is equal to 1, n is equal to 2, n is equal to 3, so why do they do what they do? Well, electrons will want to be in their lowest energy possible. And as I kind of go down here, that's actually closest to the nucleus and its lowest energy. So kind of that energy of an electron and its position relative to the nucleus are connected. So we call that the ground state. Okay. So in its ground state, an electron has the lowest possible energy possible, and it's very stable. It's happy. It's reclining on the couch. It's in its ground state. So actually, when we get started, that's a lot of water, Daniel.
It is.
This
summer when I was working, I was like in Thailand before lunch. I was peeing a lot.
Well, that's good. They say so. TMI, but very good. So when we start to, I call it find homes for electrons, see how electrons are configured, how they're hanging out, we're actually going to focus on electrons as they are all as comfy and cozy as possible in their ground state. Now, excited state, when I think about excited state electrons, all sorts of things come to mind, including light bulbs. Okay, how do we get light? And it has to do, I think I might have mentioned before, it has to do with basically electricity, running through a gas that's in that light bulb, and electricity is exciting these electrons, exciting the electrons to an excited state, which takes energy, which is provided by electricity, and as they fall back down, they emit the light. So that's kind of how that works. So excited states are great. The other thing about excited states is that I think of like fireworks. So the whole thing about fireworks, I probably already said this before, but I think it's so cool. So in order to get the different colors of fireworks, actually it's limited to kind of what electrons are going to do. So you pick a metal that's going to give you the color that you want, okay? And then that's what you're going to put in your, I don't know how to make a firework, but you have to get it out the loft, and then it has to have the right timer, and then it has to basically energize the electrons around that atom. They'll get excited, and then as they fall from their excited to their ground state, that's when they emit that discrete colored light. But it's quantized, so it's going to be only a specific color. It's not like you get a rainbow of colors. It's a discrete step. It's like a physical step, in a sense. Also, when I was thinking about instability, the thing recently that you guys have dealt with that was unstable were those little packets, where, it was a supersaturated solution. We also call that unstable. Anything that's unstable, think of it as being tentatively where it's at. So it doesn't want to stay there. Okay, so an excited electron doesn't want to stay there. All right, here we go. So there's some vernacular, like words that we're all going to have to be on the same page with regard to electrons and the energy of electrons. The first one, oh wait a minute, I guess it's coming up. The first one is electron orbital, but before I get to that, electron orbital is, remember beginning with Rutherford, that had the kind of the purple atom? Beginning with Rutherford, we knew that the atom was arranged so it had the nucleus in the center with the protons, and then electrons outside. Okay, so where the electrons are is called the electron orbital, basically. So an electron orbital is a location in space where you're likely to find an electron. Okay, and as we study this, I'll hope to try to convince you that if my fist is the nucleus, we might find electrons here. We might find electrons here, but actually, I don't know if you caught that, here, I'm trying to make a sphere, and here, make a sphere. There's actually some regions around the nucleus of an atom where you're basically zero probability of finding any electron, okay? Because the energy is quantized. The location is quantized. It's kind of set in stone, in a sense. Even though there's some wiggle room, you have to use the whole calculus thing to kind of think, I don't know, it hurts my brain, but. All right, this is where I thought we were. So electron orbitals. So when we talk about electron orbitals, we are going to use a box. So here is my electron orbital. This is an orbital. And right off the bat anyway, for the next couple of days, that's an orbital. I want to use arrows to indicate electrons. So anytime you see an arrow, that's my electron. So I'm going to show an electron here. There's a lot in this one sentence on this one slide. Electrons are located in orbitals. We're going to use arrows for electrons. A maximum of 2 electrons per orbital. So if my box is my orbital, I can put 2 electrons in there, and I'm gonna. But notice the last part of the phrase says, if I max out with 2 electrons in one box, which is an orbital, they need to have opposite spins. So the way I show opposite spins is a little cheesy, but I'm going to use an up arrow for one spin and a down arrow for another spin. So that's all to say like this. Okay, so there I have one orbital, which is a box. I'm showing 2 electrons in that one orbital. That's it. It maxes out. Man, we have a long way to go. That's just 2 electrons. If we consider like atoms here, if you go up to atomic number like 92, like uranium, we need to kind of accommodate or see how electrons are hanging out for 92. That's 2. And 91 to go. So that's kind of getting a sense for kind of where we're going with this. So the up arrow, the down arrow are showing opposite spins. Just so, and it'll be like, gosh, it might be Friday till we get to this, but we're going to see that the spins actually have values. I'll go ahead and tell you here in a minute. Tell you now. This one that's up arrow, I'll do it this way. This guy is going to be m sub s, that's the spin value, is equal to plus 1/2. And this guy pointing down is going to be the spin value. For the spin value, it's m sub s, and it's going to be, guess what, minus 1/2. We're going to ultimately kind of give numeric values to how electrons are hanging out. All my numbers. Either you don't have any calculator. Okay. So that's one of the sort of things that we're considering when we're talking about how electrons are. So orbitals, that's the box. Orbitals are grouped according to subshells. Okay. So subshells, I think I'm going to do the board here so I can add to it. How do I say this? You guys have seen this before. I know you have. So let's see. I'm going to do it this way. I'm going to do this as energy, and this won't get me very far down the road, a little bit. So this is increasing energy. Have you heard of an S? I bet you have. An S-type subshell. Okay. So these are my subshells. Goodness gracious. So an S-type can only have one orbital. A P-type, and if you've done much with this, you're like, oh my gosh, I can't believe I'm going to have to do that again. A P-type subshell, these boxes are orbitals, has 3 orbitals. A D-type subshell, and it's all about oddsies. Now we go to 5. That's a D-type subshell, and an F-type subshell, you know what I mean. F-type subshell has 7. And the longer I do this, the worse my boxes look. But those boxes are orbitals. Okay, so those are subshells. And this says that orbitals that are in the same subshell have exactly the same energy, which is kind of fun. So we could pick on these 3 P guys, and they all have the same energy. That's all that's saying. Okay. So I think I'll go over here. Now, do you remember a little bit ago when we had kind of like, this is, I'll put nucleus, this is my nucleus, and I had, you know, n is equal to 1, n is equal to 2, n is equal to 3, okay, this. So those were my principal energy levels. Those are my principal energy levels. Okay. Principal E for energy levels. All right, so I'm gonna put these two together here momentarily. So I'm gonna take a look, hopefully this video works. Let's see. Oop. Time for pointing to like those 6 electrons around a carbon atom. There's a degree of uncertainty with regard, we totally know its location and its energy at a given time. All right, so back to finding homes for electrons. So it's like if you want to mail somebody, which is a bargain these days still, if you want to mail somebody a letter, okay, most of us, I was going to say, don't have to worry about the country. The country's, well, maybe the country's going to be, might be Italy, might be the United States. And then you go from there, kind of narrowing it down to the person's specific mailbox. That's kind of what we do for electrons. So it kind of goes like this, where this could be, let's see, this would be, well, let's just say it's all in the United States. So this is the state. Okay, so it starts out broad, assuming it's a US thing. And this could be the city. Okay, and then this would be the street. And then this one would be the address, the specific address. Remember a little bit ago when I had an up arrow as a +1/2 and a down arrow was a -1/2? I call those M sub S. Remember that? So that's the nitty-gritty. But before that, we need to say where the box is, okay? And we need to say, well, that's kind of how it goes. So right off the bat, so you know M sub S. M sub S was the spin. And N is this guy over here. N, principal energy level. Okay, so that leaves the L, angular momentum quantum number, and the magnetic quantum number. So let's kind of start to kind of find our way through that. So when we talk about, I told you that as we're finding homes for electrons, we're going to basically distill it down to numbers. So we have rules for these numbers. So what's this symbol right here? Infinity, yep. So your principal energy quantum numbers can have values literally of 1, 2, 3, 4, 5. Can it have a half? No. Can it have 0? No. Can it have a -1? No. All the questions that you guys have answered, those are rules to quantum numbers. It's a quantum number. N is a quantum number. These are principal energy levels. Right? And so, like this says, it's kind of like I've drawn over here. On average, the higher the N, the farther it is from the nucleus, and the higher the energy. So I could go ahead and put a little increasing energy here, increasing energy, like that.
So it would be like N1 would have only S subshells?
We'll get into that. Yeah, we'll get into that. But we are going to definitely have to combine this with that. Cool. So this is the principal energy levels, kind of how that works. Positively charged nucleus, where the electrons can be at N is equal to the different values. Here's one for you. We talked about the periodic table. We talked about groups and periods, right? And this is a pretty not bad periodic table in that over here it has this number far to the left, and that's the group number. So what this says is, and a little bit ago I talked about those blue electrons. Those were what we call the valence electrons. It says which principal energy level N are your valence electrons going to be, and all you got to do is look at the period. So for instance, we pick on period 3 because they're kind of simpler. All of these guys, if we look at how their electrons are hanging out, their valence electrons are going to be in N is equal to 3, and principal energy level 3. Okay, these guys, N is equal to 4 for the valence electrons, N is equal to 5, N is equal to 6. And remember, the way these guys go is this lanthanide inserts right here, so they would be actually, their valence electrons would be N is equal to 6. These guys, valence electrons would be N is equal to 7. So that's something to stick the back of your head? Okay. Now the angular momentum quantum number, let's look at what the possibilities are and then we'll see how it relates to what we already know. So here's the possible values. Now does it have an upper end? Can it go to infinity? And this kind of goes back to what Logan was saying, maybe. So this is, and I think I'm going to have to kind of fix this either Friday or next week, but for now, when n is equal to 1, my possible values of the L value can be 0, 1, 2, 3, 4, 5, all the way up to n minus 1. What is 1 minus 1? It's not a trick question, it's 0. So honestly, the only L value we can have here is 0. We're stuck. Does that make sense? Because this is the rule. When n is equal to 1, so you time the n minus 1 and you substitute 1 in for n. 1 minus 1 you told me was 0. So the upper end is 0. So it starts at 0. The upper end is 0. I got 0. So let's do when n is equal to 2. When n is equal to 2, my possible values of L, what's my upper limit of when n is equal to 2? What's 2 minus 1? 1. So I got 0, 1. Okay. L is equal to 0. L is equal to 1. How about when n is equal to 3? That's my upper limit. 0. We're good with that? What about, we'll do 4. Yep. L is equal to 0, L is equal to 1, L is equal to 2, and L is equal to 3. Okay with that? Okay. So remember that's so we said that the N was the city, the N was the state, the L is the city. And these actually are going to give you orbital types. And these are your orbital types. I know it said subshells, but these are your orbital types. So just to kind of finish that, because if you're like me, you're like, how does that work? This is L is equal to 0. This is L is equal to 1. This is L is equal to 2. And this is L is equal to 3. That's it, man. And I have slides to kind of roll that out in maybe a more organized way, but that's the real deal. So, here we go. So you probably came here, and my bills are kind of weird. You might have had already exposure to this whole S, P, D, and F thing. As they're listed up there, S is the simplest with 1 orbital. P has 3, D has 5, F has 7. Okay? And then here are the corresponding L values. 0, 1, 2, and 3. And if you're like me, why put a number with something we already know as S, P, D, and F? Well, I don't know. That's just the way we do it. Okay? Now, the reason there's a dotted line there is because you can definitely have these other guys. It goes on. Et cetera means, yeah, we just keep going on. I'm not sure what these would be. But we talked about ground state and excited state. And the way this works, we're working with ground state. Notice I'm pointing to my SPD tab. When we're finding homes for how electrons are hanging out, S, P, D, and F will accommodate up to everything we have on these guys right here. Even needs 118 electrons around this guy. When the dust finally settles to find homes for those 118 electrons, you're not going to have to go beyond an F type. Okay. It's funny when I say that, I'm like, are you sure this is not? Yep, that's true. But they're there, they're waiting in the wings for an electron to be excited out there. So L is equal to 3. This guy right here. And if you're like me, I kind of learned it like SPD and F, and so I have to translate that. L is equal to 0, L is equal to 1, L is equal to 2, L is equal to 3. Those 4 orbital types. All right. Well, this is kind of fun then. So I am gonna, if it's okay with you, I'm gonna go over here, and I am going to, I don't know if I'll do, if I have patience to do it for all of them, but I'm gonna go ahead and do what we know about this, and I'm gonna put it here. So for instance, n is equal to 1, the only type of orbital type we can have is the S type, and I'm gonna put, here in a minute, I'm gonna call this 1s, I'm gonna put 1 box. N is equal to 2, I can have a 2s, which is 1 box, and I can have a 2p, which is 3 boxes. N is equal to 3, I can have a 3s, 1 box, 3p, 3 boxes, 3d now, which is 5 boxes. And again, I'm going to have to kind of fix this when we meet again later, but it basically works. When n is equal to 4, I know I can have L is equal to 0, that's 4s, 1 box. L is equal to 1, that's 4p, and n is equal to 4. 3 boxes, 4d, 5 boxes, and then we get really exciting here, 4f, 7 boxes. Yay! So that's it. This says that orbitals with identical n values and identical L values make up what we call subshells. And this goes on in that same idea to say, and you can almost see it as I have it written here. If you have a set, I could pick any of these sets, any of these horizontal sets, and all of the boxes, all of the orbitals accommodating electrons would have the same energy. Kind of makes sense because this is low energy, this is high energy. So we could pick on these guys right here. We could say that these are 5 degenerate orbitals. Degenerate orbitals all have the same energy. Notice I have to be, I can't say that, and if you're visualizing, you know this is true. I can't say that any of these 5 orbitals in the 3D are degenerate or equal to energy in the 4D. No, that won't work. It has to be in the same principal energy level and the same subshell. Makes sense. All right, and I kind of said this one. So hopefully you're kind of seeing, didn't mean to get ahead of myself, but you see how that works? I like the whole visual thing. In fact, when I'm working a problem and I can answer keys, sometimes you'll see me like recreate that over there because I'm like, oh yeah, I remember how that works. Okay, so kind of visualize how this works. All right. Well, that's good timing. Check this out.